So the talk is called Research Workloads on Preemptible VMs. I'm Michael Basilian, product manager at Google. I'm joined by two friends from Two Sigma, Chris and Rodrigo. They'll give a little bit more of an introduction in the second half when they talk about their workloads on preemptible VMs. So here's the outline. I'm going to talk for a few minutes about what preemptible VMs are, how they work, and what the general concept is, and then the Two Sigma guys will tell their story. Cool. All right, so if I had to tell you what a preemptible VM is in one slide, and if there's one thing that you remember from my half of the talk, is that a preemptible VM is a regular VM, like any other VM that you can get on Compute Engine. There's just two caveats. One is that it cannot run for more than 24 hours. We limit the lifetime and the uptime of the VM for 24 hours. And the other is that we reserve the right to take them away with 30 seconds of notice at any point, right? It's right there in the name. That's what makes it preemptible. The upside of it is that they only cost 1 cent per core hour, and that includes Intel Skylakes. That's up to 80% cheaper than a regular GCE VM. If you attach a GPU to that VM, to that preemptible VM, it'll be about 70% cheaper than a regular GPU. If you attach a local SSD to that preemptible VM, it'll be around 40% cheaper than a local SSD attached to a standard VM. And local SSD, you might have heard already at some point today or in one of the earlier talks, is our high-performance attached storage for virtual machines. The other highlight is that prices are constant. There's no bidding of any kind. This is the price. What you see is what you get in terms of price. That doesn't change. Cool. So what can you do with compute that's just sort of randomly disappearing with 30 seconds of notice? There's actually quite a few things that we've seen people do. Really anything that's embarrassingly parallel or pleasantly parallel, as some people say. Anything that is high throughput or isn't composed of a lot of independent tasks that can be solved independently, where losing a single machine doesn't mean that everything else disappears. Or if you can figure out how to capture state for your computations. So Monte Carlo simulations, where different machines are solving different input conditions. Image understanding, rendering and media transcoding, anything really to do with images. If you imagine a use case where you have 1,000 images and you want to assign each of those to one of 100 preemptible VMs, to do some processing on that image. If that VM goes away because it gets preempted, you don't really lose anything except for that image, and you can reschedule that work if your scheduler knows how to handle that. And I'll talk about that in a little bit. Data analysis, of course. Our data proc product supports preemptible VMs, genomics and health workloads. If you search the web for Broad Institute preemptible VMs, you'll see a write-up of their use case. Financial analysis, of course, and you'll hear more about that in the second half. And many, many others, including physics, math, chemistry, and so on. And to be clear, people are using these to solve very real workloads. So on any given day, we have 10 to 50,000 core clusters of preemptible VMs being used, multiple ones. And the largest we've ever seen is an MIT math professor doing some research in a weekend on 580,000 cores. So this was around 200 to 300 core years of compute in a weekend. Okay, using them is relatively straightforward and easy. There's just one flag that you have to do. Like I said, they are like regular GC VMs. You configure them like a regular GC VM. All you do is add a -- preemptable to your command line, or in the UI you just select preemptibility on, or in the API you select preemptibility to be true. Generally, of course, you're going to be creating more than one of these things, and so that's where things get a little bit more interesting. But fortunately, there's a lot of tools that make it easy. We have our GCE managed instance groups that can help you manage instances of preemptible VMs and recreate them once they get preempted. We have a published solution on our website for how to use htCondor, which is a very popular job scheduling tool with preemptible VMs. Kubernetes and GKE, of course, support preemptible VMs. And in the second half, you'll hear more about Two Sigma's Cook job scheduler that supports preemptible VMs as well. So I wanted to give you guys some best practices for how to use preemptible VMs to make the most of them and to minimize the preemptions. So like old school telephone companies, nights and weekends are best. Obviously, you want to avoid times when the data centers are busy. You want to architect your system for regular preemption. You should expect that preemptions will happen. They're not a one-off rare situation. We see on historical rates 5 to 15% preemption rates. You should know that this will change as a function of the VMs that you build, the zones you use, and time of day. And of course, you should be prepared to move regions and zones if preemption rates get really high in a place. But that's good cloud practice anyway. Beyond that, use shutdown scripts and checkpoints to save state if that's appropriate for your workload. I'm talking about standard GCE shutdown scripts that are just part of Linux. The smaller, the less choosy the VM, the less likely it is to be preempted. So a 64-core preemptable VM with local SSD and GPU is much more likely to be in somebody's way than a 16-core preemptable VM. On the website, we also have a bunch of best practices that outline a lot of this with a lot more detail than you can read. Cool. And I'm going to turn over to the 2 Sigma team.
Good morning, everyone. I'm Chris Fortier with 2 Sigma. So I'll talk about a bit about our research workloads on preemptible VMs. So quick disclaimer, even though we're at a technology conference, most of us are technologists, we work at a financial firm, so we are not here to talk about selling or solicitation of securities or instruments. We are not giving you any stock advice, et cetera, et cetera, et cetera. Really just talk about our technology story. So who are we? So I'm Chris. I was formerly the head of private cloud engineering at 2 Sigma, currently the head of public cloud engineering. A lot of that work really is figuring out how do we adopt cloud computing and bring it into our company, especially the native services, which are really interesting for us. In a few minutes, you'll hear from Rodrigo, also works on my team. He spends a lot of our time figuring out our distributed compute environment using GCP. A lot of it is on preemptible virtual machines. So on our section of the agenda, we're going to talk a little bit about batch research and what that means to us and how we do it. A little history of our distributed compute environment and give you a taste of what it looks like today. A bit about how we build platforms on GCP, and then some of the challenges and takeaways, which are kind of the interesting things for most people. So batch research process. How does 2 Sigma is a quant hedge fund, and so how does a quant hedge fund make money and survive in the world? You may envision there's a modeler that comes up with this idea. Oh, eureka! Here's how we're going to make money. Draws a technique on a whiteboard, and poof, it becomes production, because that's how it works in the movies, right? So not exactly. The modeling workflow actually looks fairly similar to like a typical developer workflow. There's an idea of what they want to do. They do some work with it. They do some data analysis and shifting of data to figure out what makes sense. And they try to write some techniques out, and then they want to simulate it. They usually research backtesting in the market, like, hey, how would this have performed over the past N number of years? And then from there, once they actually figure out, hey, this is going to actually work for us, they do a typical a review process. So similar to a code review, they write papers up, they present it to their peers, they figure it out, and it becomes a production product at some point. A lot of what we use Google Cloud for is that technique and data in the simulation area. A lot of the data analysis tools, a lot of the simulation backtesting we're running on Google today. And especially the simulation of preemptible VMs is where GCE really shines for us. So a bit about our distributed compute environment and kind of over the history over the past 15 or 16 years. As legend has it, when 2 Sigma was founded, a couple of founders, a couple of early employees, time-shared compute based on a whiteboard. Literally just on the whiteboard, hey, Bob has it this week, Susie has it next week, et cetera. And I guess it worked for a few years, at least 3 years or so, from what I'm told. Early 2004, the team decided to work on an internal scheduling system. Really just, we want to be technologists. We want to figure out a better system than a whiteboard, quite frankly. So that worked well for apparently 8 years or so, the internal one. And around 2012, Mesos came on the scene and really captured our attention. It solved a lot of the really interesting, lower level problems. How do you do resource management? How do you do scheduling? Those are the types of things like, how do you execute a job on this host? Isn't something that is a core competency of what 2 Sigma wanted to be or wants to be. So we really adopted Mesos full speed with that. But we still want to maintain its fair share of scheduling things. So even back in the early days of the whiteboard, we were like, hey, we want efficient utilization. We want it shared across everyone. So we decided to write what is now known as the Cook framework, which is a framework for fair share scheduling of jobs on Mesos. And we've been using that ever since 2012 when we first started writing it. So 2016, cloud computing 2 years ago was definitely a mainstream concept. We decided we really wanted to start working with that and figuring out how do we use elastic capacity. Up to that point, we'd always had physical data centers. Everything is, here's the hardware, here's what we can use. So we started making a lot of changes to connect our data centers to the cloud and then changes to Cook and Mesos to work in these environments. And then now, mid-2018, we have real dynamic cloud compute, which has really been very beneficial for us to be able to say, what is our workload, what can we do? We're not limiting our modelers based on the compute that we can get to them anymore. But there's a caveat, though, that we're going to talk about in a minute about even though we have elastic dynamic compute, we don't have dynamic storage or networking or other things still. We have a talk about it in a few minutes about how we're still running hybrid cloud with Google and our data centers. There we go. So a little bit of capacity over time, which kind of just symbolizes what I just mentioned, where over time is a very step function. You know, on this date, we decided to order a whole bunch of servers and put in a data center, and that's how it lasted for, I don't know, 15 years or so. And mid-2016, you start to see a lot of dynamic spikes based on user workload. This is really when cloud computing became a thing for us. So one, it opened up compute ability for our modelers, but also proved a theory that we had years before, is that our demand isn't linear. It's not here's what we're going to use today. It's a lot more opportunistic based on what phase of research somebody is in. And then, yeah, that's that. So that's a bit of the history. That's about how we got today. But what are our users? So if we think about Rodrigo and I, we work in what's called platform engineering. So we deal with a lot of the lower level. How do you build a system? How do you get resources available to somebody? And there are teams above us. So we think of modeling engineering, which is the next step above us that use our platform as a building block. Modeling engineering does a lot of stuff to work with techniques, with data analysis, a lot of like how to run a simulation. Then above them, we have quantitative engineers. Quantitative engineers, they work a lot closer to the modelers, and they work with actually writing the models, actually writing techniques, writing tactics, writing the actual code that will eventually do trading. And then finally, we have modelers, who are researchers that are going through trying to find information that is tradable and actually usable. So we have a bit of a description of kind of the workloads, and this is where fair share scheduling actually comes back to us and is kind of important, is that even though we have all the dynamic compute, I mentioned we don't have dynamic storage, we don't have dynamic networking yet. So we still want to be able to fair share our resources with people, and we also still care about things like quotas. We still care what the bill looks like every month. We care about a lot of those types of things. So when we think of the workloads that we're running, again, modeling engineers who are building just right above us, like they're doing scheduling, cook schedulers, they're doing other things, they need a little bit of capacity. You know, a few hundred gigabytes, a few tens, 20s of vCPUs to test out their work. The folks doing the quantitative engineers, though, because they're working closer to models, they actually want to test, like, hey, does this model actually work? Like from a technical standpoint, they need more. They need to do more testing. And then our modelers, there are probably an infinite number of data sources and things to trade on in the world, and our modelers want to run every single one of those, which of course isn't possible. So they are the highest demand of usage across our company, which actually these slides all are showing that, kind of this, like, what we see from our internal usage patterns. So, and on that note, I'll turn it over to Rodrigo to talk about how we actually build platforms in GCP.
Thank you, Chris. So, you know, Chris just talked about how the environment has evolved over time, and also capacity, how it used to be this like very nice step function, and in recent years it's more like bursty, and also how we view our users, how they share this platform. And you know, we can think about all of this as like very cool data, and we can do some more analysis and dig into it, or we can take that as requirements, which is what I think we've been doing for the last 2 years, right? So when you think about this environment, we really have like two requirements. One, following the assumption that demand is very bursty, we need to be able to scale up and down, automatically, and two, like everyone is sharing this platform, but everyone has different needs. So we're not in a position where we kind of impose people what resources they get. We want, this cluster to be driven by demand, right? And as we started to move these workloads to the cloud, we kind of came up with two guiding principles, right? The first thing that I want to talk about is security, right? We take security very seriously at 2 Sigma. As you can imagine, this environment is one of the most sensitive ones because it has some good stuff going in there. So we stick to GCE and some core networking products like interconnects to provide connectivity back and forth between 2 Sigma and GCP. I'm not going to talk more about security in this presentation because other guys, Nick and Michael from 2 Sigma are giving enough talks on the topic. The next thing that I want to talk about, though, is kind of the other thing that we always try very hard to keep in mind, which is elasticity, add value to the users, add value to the business, and do so in a cost-effective way. Because we've been operating data centers for 10, 15 years, we know how much it costs to run these environments, right? And we cannot just go to the cloud and start like spending money like crazy because it's this shiny new thing or like because everyone is doing it. We have to be able to add real value, and we need to be able to do that in a cost-effective way, right? Now, preemptable VMs and custom machine types is what really allows us to do that. We get the 80% flat discount, and then with custom machine types, we create exactly the resources that Cook needs. I'm going to talk more about Cook, but that Cook needs to schedule these jobs. Now, this is a fairly large environment, and I don't want to be on the hook, creating and deleting VMs all the time. And Chris, I'm sure, doesn't want me to be on the hook to do that. So we need an autoscaler, which is a product that we've been working on since early 2016. So now, if you take the autoscaler, you take preemptable VMs and you take custom machine types, now you get all the kind of building blocks to build this platform where you can scale to a couple of 2 sigma data center sizes for, let's say, a single user, right? Before 2016, they had to share all this platform between each other. Now it's just a matter of like putting stuff in some queue, and then you're going to get capacity eventually. But before talking about autoscaling, I want to talk about Cook a little bit, because Cook sits at the top of the stack, and without Cook, there really isn't much, right? What are these VMs good for if nothing is running on them? So Cook is a Mesos framework. Early versions were developed back in 2012. It's open source. And it has this like very core concept of fair scheduling that we've used that we use both on-prem and in the cloud, but just for different reasons. Fair scheduling essentially just guarantees that no one user takes over an entire cluster, which is super important when you're running on-prem. But let me give you an example. I think it's going to be kind of a lot easier to understand than just me talking about it. So suppose user Red here has been running overnight a bunch of jobs, right? And he got lucky, he got the entire cluster. But it's 7, 8 a.m. New York time, and now we have like 3 modelers that want to run jobs. There's one kind of obvious problem here. There's no capacity to run all these additional jobs. But there's another problem, right? Let's say we make up some capacity somehow. Now we need a way to determine who goes first. We can do some kind of round robin, we can do first come, first serve, we can do random, or we can do kind of fair sharing, which is what Cook does. So essentially, it's going to take this virtual queue. So each one of these 3 virtual queues, it's going to merge them into one global queue, and then it's going to order them by fairness. And fairness here means it's going to look at what's your current usage. What's your backlog, and then based on that, it's going to determine some kind of ordering. Then on the background, it's going to preempt some of Red jobs, and then it's going to schedule everything else. There's a downside to this kind of situation, which is, Red is, we lost some computation time that we've already done. But it's not a big deal, and I think it's much better than just making people wait. Eventually, those jobs are going to get back, are going to get put back in the queue. Now, you might be thinking, like we're at a cloud conference, why don't you just create more VMs and be done with it? You don't need to preempt anyone, which is kind of fair, and it kind of works in theory. We're less constrained with capacity. We have access to more machine types, but now by having this elastic cluster, we created a problem for ourselves, right? Now we have this ramp-up latency. So suppose there's 10,000 jobs in the queue, and somehow we magically decide that we need 1,000 VMs. If I send 1,000 requests to GCP, well, first of all, there's API rate limitings, right? So I cannot just fire 1,000 requests all at the same time. And then there's no guarantee that I'm going to get 1,000 VMs right now. And even if I could get them right now, remember, we work in a very secure environment. These VMs need to get an identity. They need to register to other security services. They need to register to Mesos. And then Cook eventually needs to schedule these jobs. So all of these kind of steps, they take time, a couple minutes here, a couple minutes there, and then when you add up everything, it's time that is non-negligible, and the user can actually feel it. So we want to avoid that. And Cook and fair sharing is what allows us. It's kind of the thing that we use to solve this problem. It allows us to share resources as they come up and as they become available. So now that we talked about Cook, we can start talking about autoscaling because Cook and the autoscaler work together, and it's kind of the next logical step in the stack. So I think I mentioned this before. The first version, we wrote it in 2016. Kind of one of the reasons why we wrote the autoscaler is because we wanted to have a deep integration with the rest of the Two Sigma ecosystem, in particular Cook and Mesos. And then we also wanted to take the opportunity to give Cook the right resources by creating the right machine types. Over time, as we iterated on Launchy, we've started to use more and more and more custom machine types, and now we're at a point where we almost exclusively use custom machine types. And then the other thing is as the usage of the cloud grew, as we started to move more and more workloads into the cloud, we had to expand to multiple regions, and we had to expand to multiple zones to try to avoid preemption. And we had to write some code here and there into Launchy to be able to kind of chase this capacity, right? Because you can have a pretty large cluster in one zone, and then you could lose some percentage, but you still have the jobs, so you need to run those jobs somewhere. And Launchy allows us, Launch and Cook together, they allow us to do these type of things. High-level overview of Launchy is essentially big loop. First thing that we're going to do is check for idle or unhealthy VMs. This is essentially scaling down. If the VMs are idle, just scale down. Then we're going to look at the job queue in Cook. If there's something, we keep it in memory. Otherwise, we just stop scaling. Then we check for what we call limits. Limits here could be GCP quotas, could be internal limits like don't spend more than X amount of money per hour. Don't create more than X number of VMs on a given time window. Because remember, they have to talk to internal services. These services are kind of developed for or are kind of set up for some maximum peak load, so we cannot just start hammering them. If all the checks are good, if all the checks and balances are good, then we compute what we call a runnable subset of jobs. That essentially is, look at the job queue. Let's say I'm a user and I have a quota of 1,000 jobs, and I already have 500 jobs running. If I put 2,000 more jobs on the queue, obviously only 500 are going to get scheduled, so we don't want to create resources for 2,000 jobs. We only want to create resources for 500 jobs. So that's what the runnable subset means. Now that we have the requirements, we can actually go and compute the machine types that we want to use. The input of this function is essentially just the list of requirements, and the output is almost a fully well-formed payload that we can send to Google. So it's something like create 200 VMs of type X and another 150 of type Y and something like that. And then the last thing, to kind of wrap it up, we need to know where to put these VMs. So the last step in the scaling loop is figuring out where to create these VMs. We have the payloads already, and we send a request to Google. Hopefully, we get everything that we wanted, and then we write some more metrics to do further analysis offline. Or, we're going to use these metrics also on the distribution calculation in the next loops. So if you put Cook and Launchy together, this is kind of pretty much what you did. This is an intraday graph of capacity. In Two Sigma Teal, you have the used resources, and I don't know if you can see it here, but there's a little spike in green, which is provisioned resources. So there's usually a little discrepancy between what we create and what's actually being used, which is not a big deal. I think we're okay living with that. But I think the more interesting things here is kind of the fact that this graph, well, clearly is very spiky, right? And the spikes are very short-lived. So this data validates our initial assumption that demand is very bursty and that we should not have this kind of fixed block of resources, business hours, New York, or 24/7 or something like that. Now, what's more annoying about this is the fact that things like what's your average cluster size doesn't really make sense here, right? I can give you a global max over the last 6 months, some kind of local max, interweek or something like that. But, average utilization or average size don't really make much sense. And beyond the technicality that, I cannot give a, straight number, this is important because, all these resources talk back to services in Two Sigma, and people have to do capacity planning. They need to know if, they are going to have, if their service is going to have, 10 replicas or 20 replicas. And it creates these frictions, right? Because on the cloud, we're doing these things where we want to scale up as much as possible. But internally, people have limited resources, and they need to be aware of these things. So let's talk about allocation. So if we recap, we've talked about elasticity. We've talked about how we can scale up and down and give these resources to our users. But we also need to do it in a cost-effective way. And allocation is just one metric for this. Usually it hovers between 90 to 95%, and we can achieve this with launch and cook. But there are these dips, right? Every once in a while there are dips. And you might be thinking, what's the deal with that? Like these guys wrote an autoscaler and they wrote a scheduler and they still have like these pretty bad inefficiencies. But they are explainable, and it's really because the one thing that we try to optimize for is to never have a backlog. We don't want to be, we move to the cloud and we don't want to be in a situation where someone has to wait for resources. So granted, we have some kind of restrictions in how fast we scale up, but we try to push that boundary, as far as possible, to kind of provide a good user experience. So let me give you an example of kind of how you can end up in this situation. Suppose at T0, nothing is happening, a couple of jobs running on a single VM, we're at 100% allocation. Say at T1, a user comes and they want to run a couple of workloads or a couple of jobs. Now we have a backlog, and this is exactly the situation that we want to avoid. So Cook and Launch start doing their thing. They create some VMs, they bootstrap, they register to Mesos, and Cook schedules that. And now the user is fully running. We drop to 90% allocation. For whatever reason, there was a little inefficiency. Not such a big deal. But this is when it gets interesting. Let's say half a day goes by, and now we're at T50. Most of the jobs finished, but there's still one job in every single VM. And obviously, we cannot terminate this VM because we don't want to waste this progress that we've made. So we keep them alive, and this is when you see the dips, and this is when allocation drops to 25%. But there is like a twist to kind of this example. Let's say really most of the jobs finish. We terminate the VMs that were fully idle, but there's still one VM with one job running, and we're still at 25% allocation. Right? So what actually happened here? What we found out over time is that just looking at this percentage at face value doesn't really make much sense, and it doesn't give us the full picture. Right? It's not the same thing saying we wasted 75% of a 100,000 cores cluster than saying we wasted 75% of a 500 cores cluster, right? And we rather look at the CPU hour and memory hour and kind of rate that we paid for, but we didn't actually use, rather than just looking at this number. And the other thing, but more importantly, I think, is the fact that you have to keep in mind that we want to avoid having a backlog at any time. We don't want people just waiting for resources. So this allocation thing is the second kind of priority. We optimize for it, but we don't put that. We don't try to look good on paper over users having a good experience. And this is just one of the many challenges that we have kind of on a daily basis, and that we have to deal with in this elastic environment. But there's many, many more that Chris is going to talk about.
Hello again. So we only have a few minutes left. We know that we are the last thing sitting between you and lunch, so we'll try to get through these fairly straightforward. So we talked about a lot of the interesting things and the problems we've solved, but our big challenges so far and what we have left to solve. A lot of it does stem from being hybrid cloud, in that we're using dynamic compute in Google, but all of our data stores are still on-prem somewhere. It's still a SQL server, it's still an HDFS cluster, and getting all that data from our data center into Google to do any computation is a challenge, and we're still working through the right way to solve that one, especially with back pressure as well. So the ability to spin up a 5x data center is great for our users. Like they love that ability. Our network team, our infrastructure teams, they don't love us when we do that. They tend to get very upset when we DDoS their services because of our users. So solving those types of things, solving QoS, network fair share is something that we haven't even looked at yet. So those are some of the things to really solve and figure out As Michael mentioned, checkpoint and restore. So we talked about 15 years of history of Two Sigma of how we've done research. Some of the stuff that was built 10, 12 years ago, we're still running, and it doesn't necessarily support checkpointing. It doesn't support restoring. So in those types of use cases, it's there's stuff we can do from the engineering side, but there's also stuff we go talk to our users to figure out, can their system handle it? Can they go rewrite and add a feature to checkpoint to somewhere, and then figure out how to make their life more dynamic? So some of the takeaways. To get through those, we are able to do a lot of things now that we couldn't do before. Like I said, the ability to spin up data centers with just by an API call, the optionality of it. What's the ability for me to land a TPU in a data center? It's none. It's not possible. But with Google, I can just make it an API call. Oh, add a TPU here. Add 50 GPUs over here is something that our modelers are really, really looking for, and it opens up a ton of research possibilities for them. Our investments in things like Cook and our Autoscaler have really paid off and opened a bunch of value. But then the takeaway is also hybrid cloud introduces a lot of frictions, which a lot of people have talked about, like trying to operate both environments. There's many unsolved problems. And then improving scheduling is a never-ending quest. A lot of the optionality, custom instance types, for example, isn't something that we had 2 years ago. So the idea to go through and say, oh, I want X number of CPU, X number of RAM is a really interesting feature, but every time these come out is another optimization that we can make in our environment. The obligatory, we are hiring across the platform engineering teams, our cloud security teams, and even some of our data teams, the teams that are actually using some of these services really hardcore are also hiring. We have lots of opening. We actually have the slide earlier. There are about 9 talks by Two Sigma this week. Feel free to check out some of the other ones. Some of them are more PE focused. Some of them are more security focused. Some of them are more data focused. So we recommend going to see some of those. And then last but not least, thank you. I think we have about 5 minutes left for Q&A.